Effective management of the environment is increasingly science-driven, and this important research is taking place in Ireland's universities.
There are an array of research projects throughout the country of different sizes and with different organisations and different universities, covering all the different thematic areas such as climate change, water quality, waste resource management, biodiversity, socioeconomics.
Some examples of this STRIVE research are underway in County Galway, two projects that may be the key to revolutionising wastewater treatment in Ireland and abroad. Just outside Tuam, NUI Galway have set up a water research facility at the site of the existing wastewater treatment plant. It's a full-scale testbed for innovative wastewater treatment technologies. This system, developed at NUI Galway, is the only one of its kind in Europe. Wastewater from the channel in Tuam is put through a system of tanks, as project engineer Edmund O'Reilly explains.
The primary tank 1 and 2 and the balance tank, they're essentially settlement tanks. So when the raw wastewater comes in, the solids are settled in those tanks. What we have here is a scale model of the system, reactors 1 and 2 here. In each reactor we have this plastic media which the bacteria grow on, so we provide a very large surface area for the bacteria to grow on. When reactor 1 here is full, we have the bacteria exposed to the water where they take in the nutrients from the water, and that's how the water is treated. Submerging the bacteria in reactor 2 now so that they have access to nutrients, and we're exposing the bacteria in reactor 1 so that they have access to the oxygen in the atmosphere. So we have no forced air, we have no compressors. The advantages of that are we're up to a quarter of the cost of similar systems in terms of energy usage. Maintenance here is very simple. All you have is a set of pumps, really. Your media will be fine on its own in the tanks. And thirdly, then, the operation is very simple. You're just controlling pumps over and back.
Right. So all of these tanks here we see, would these be typically underground in a normal situation?
Normally they're underground, yes.
Right.
What we have here, we have kept them above ground so we can bring technologies here that can be tested from lab and pilot scale and ultimately bring them to commercial scale.
This technology is suitable for villages and small communities all over the country, guaranteeing quality effluent treatment while reducing energy consumption. What's the benefits to Ireland with this project?
The benefits to Ireland with this project will be the development of new technologies in the water and wastewater sector, which will lead to a safer environment firstly, but also lead to major exports, job creation into what is a huge market in Europe and the US and worldwide indeed.
Back in the lab where this project began is a hive of innovation when it comes to treating wastewater. What's left after treatment at the water research facility is pure clean water. The treatment of sewage wastewater is a big issue in Ireland, and it takes a lot of energy, which is costly and has environmental impacts. It's difficult to imagine how this waste could become a major energy source. Another research project at NUI Galway is focused on harnessing this energy.
We focus on anaerobic digestion research for wastewater treatment, and essentially what's different about it compared to, let's say, conventional, the aerobic technologies, is that instead of just treating the wastewater, we're actually recovering energy from the wastewater during treatment.
So what's the difference between aerobic and anaerobic?
The main difference is that in one type of wastewater treatment system, oxygen or air is pumped in. And to pump in that air, you require quite a lot of fossil fuel to run the pumps. It's very expensive, and they produce a lot of biosolids, or waste sludges. And these sludges themselves require treatment and disposal. They need to be transported to where they're ultimately going to be stored. And that costs money, and it means that these aerobic systems have a very large carbon footprint. The alternative approach is to use the anaerobic approach. You reduce the carbon footprint and biosolids by 90%, and you also recover energy.
So when you talk about this breakdown of sewage, is it bacteria or what's going on in the process?
Essentially, it is bacteria, and the anaerobes are unusual in that they convert the carbon compounds that are in sewage. These are sugars and proteins and plant materials, for example. They break down these materials as part of their natural growth. But the advantage from the anaerobic point of view is that the end product is methane, so it's a usable end product. And essentially, really, approximately maybe 80 to 85% of the energy that's contained in the wastewater is conserved in the form of the biogas.
Biogas like this is methane, the same as natural gas. We can use it for transport and to power and heat our homes. So when the sewage now you're testing here in the laboratory, where does that come in and how does this actual process work?
Well, what we're looking at here is our lab scale systems. So these are small 5-litre anaerobic digesters. And what happens is that normally these reactors are operated on an upflow basis. So the wastewater is pumped in at the bottom of the digester.
Is the sewage?
Exactly. It passes up through the bacteria, and the bacteria form these aggregates here, so they clump together. The wastewater comes into contact with the bacteria, and the bacteria do this tremendous job for us. They remove the pollutants and they produce the biogas. And for the last 20 or 30 years, anaerobic digesters that have been used for these purposes are heated. And they're heated because these guys, the bacteria that actually carry out the transformation, they need normally to operate above 30 degrees centigrade. The problem with the sewage is if you try and heat an anaerobic digester to that temperature with a dilute wastewater, you end up having to put more energy in than you can recover.
As a solution, Professor Vincent O'Flaherty and his team have developed a low-temperature anaerobic digestion process able to function at the average ambient sewage temperature of 12 degrees, suitable to Irish conditions. So Vincent, are there different bacteria operating at different temperatures here?
There are, Duncan, and what we've been doing really is looking and researching at what are the best bacteria for the low temperatures, and then we develop the best inoculum for our reactors. And essentially what we're talking about here is natural selection. There are hundreds and indeed thousands of different bacteria that can do this job. And when you apply a particular wastewater at particular temperatures, those most adapted will eventually develop and grow.
So Darwin's theory, survival of the fittest?
Absolutely, at a microbial level.
If you imagine the amount of sewage that is currently being treated aerobically all around the country, the potential for creating energy from biogas using this low-temperature anaerobic digestion process is enormous. So really what we're seeing here is all of our organic waste in the future generating energy.
Absolutely. As we begin to run out of sustainable energy sources, as oil declines and we need to develop, for example, new sources of plastics, all these other materials that we currently get from oil. And really it's the job of researchers to find efficient, economic ways of getting these valuable compounds, including the energy and the biogas from the waste.
Ireland is producing key niche experts like Vincent who are developing new environmental tools through their research, embracing a new holistic approach to managing our waters and our environment. Ireland's Atlantic waters have been talked about as the future energy source for Western Europe. The race is now on to find an efficient way to harness oceans of this energy. In our next episode, we'll explore what this will mean for our environment, energy resources and economy in the future.